Using the value of R equals 0.801 for the 23 pairs of data in table 10-1 on page 469, and using a significance level of 0.05, is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and numbers of Nobel laureates? Requirement check. The first requirement of a simple random sample of quantitative data is questionable. The data are quantitative, but examining the original data, it does not appear that they are randomly selected pairs. Because this requirement is not satisfied, the results obtained may not be valid. The second requirement of a scatter plot showing a straight line pattern is satisfied. The scatter plot also shows that the third requirement of no outliers is satisfied. We can base our conclusion about correlation on either the p-value obtained from technology or the critical value found in table A6. Using the p-value, use the p-value and significance level alpha as follows. If the p-value is less than or equal to alpha, it supports the claim of a linear correlation. If the p-value is greater than or equal to a, it does not support the claim of a linear correlation. The stat display below shows that the p-value is 0.000 when rounded. Because that p-value is less than or equal to the significance level of 0.05, we conclude that there is sufficient evidence to support the conclusion that for countries, there is a linear correlation between chocolate consumption and numbers of Nobel laureates. Using table A6 to interpret, consider critical values from table A6 as being both positive and negative, and draw a graph similar to the figure below. For the 23 pairs of data in table 10-1, table A6 yields a critical value that is between R equals 0.396 and R equals 0.444. Technology yields a critical value of R equals 0.413. We can now compare the computed value of R equals 0.801 to the critical values of R equals plus or minus 0.413 as shown in the figure. This is the sort of figure we use to determine whether or not the sample data has an R value that fits between or to either side of the critical values. If the computed linear correlation coefficient R lies in the left or right tail region beyond the critical value for that tail, conclude that there is sufficient evidence to support the claim of a linear correlation. If the computed linear correlation coefficient lies between the two critical values, conclude that there is not sufficient evidence to support the claim of linear correlation. Because the figure on the previous slide shows that the computed value of R equals 0.801 lies beyond the upper critical value, we conclude that there is sufficient evidence to support the claim of a linear correlation between chocolate consumption and number of Nobel laureates for different countries. Although we have found a linear correlation, it would be absurd to think that eating more chocolate would help win a Nobel Prize. Additionally, the requirement of a simple random sample is not satisfied, so the conclusion of a linear correlation is questionable. If we conclude that there is a linear correlation between x and y, we can find a linear equation that expresses y in terms of x, and that equation can be used to predict values of y for given values of x. Note that a predicted value of y will not necessarily be the exact result that occurs because in addition to x, there are other factors affecting y, such as random variation and other characteristics not included in the study. The value of R squared is the proportion of the variation in y that is explained by the linear relationship between x and y. Using the 23 pairs of chocolate Nobel data from table 10-1, we get R equals 0.801. What proportion of the variation in numbers of Nobel laureates can be explained by the variation in the consumption of chocolate? With R equals 0.801, we get R squared equals 0.642. We can conclude that 0.642, or about 64% of the variation in numbers of Nobel laureates, can be explained by the linear relationship between chocolate consumption and numbers of Nobel laureates. This implies that about 36% of the variation in numbers of Nobel laureates cannot be explained by rates of chocolate consumption. In our examination of chocolate consumption versus Nobel laureate data, we concluded that there is sufficient evidence to support the claim that there is a linear correlation. We should not make any conclusion that includes a statement about a cause-effect relationship between the two variables. We should not conclude that winning Nobel Prizes causes people to consume more chocolate. We should not conclude that consuming more chocolate causes an increase in Nobel laureates. Know this: correlation does not imply causality. We should use common sense when interpreting results. Clearly, it would be absurd to think that eating more chocolate would help you win a Nobel Prize. Given that chocolate is seen as a luxury item around the world, it is more likely that the same environment that allows people widespread access to chocolate also offers more opportunities for education and resources to inspire the scientific, literary, and diplomatic acts that win Nobel Prizes. Here are 3 of the most common errors made in interpreting results involving correlation. First, assuming that correlation implies causality. One classic example involves paired data consisting of the stork population in Copenhagen and the number of human births. For several years, the data suggested a linear correlation. It should be pretty clear that storks do not cause births and births do not cause storks. Both variables were affected by another variable lurking in the background. A lurking variable is one that affects the variables being studied but is not included in the study. Here, an increasing human population resulted in more births and increased construction of thatched roofs that attracted storks. Second, using data based on averages. Averages suppress individual variation and may inflate the correlation coefficient. One study produced a 0.4 linear correlation coefficient for paired data relating income and education among individuals. But the linear correlation coefficient became 0.7 when regional averages were used. Third, ignoring the possibility of a nonlinear relationship. If there is no linear correlation, there might be some other correlation that is not linear. Hypotheses. If conducting a formal hypothesis test to determine whether there is a significant linear correlation between 2 variables, use the following null and alternative hypotheses that use rho to represent the linear correlation coefficient of the population. The null hypothesis is H0 rho equals 0, no correlation. The alternative hypothesis is H1, rho does not equal 0, so there is a correlation. Test statistic, the same methods of the first part of this section can be used with the test statistic R, or the t-test statistic can be found using the following. T equals R over the square root of 1 minus R squared over n minus 2 with n minus 2 degrees of freedom. If the above t-test statistic is used, p-values and critical values can be found using technology or table A3 as described in earlier chapters. Use the paired chocolate Nobel data from table 10.1 to conduct a formal hypothesis test of the claim that there is a linear correlation between the 2 variables. Use a 0.05 significance level with the p-value method of testing hypotheses. Requirement check. The requirements were addressed in a previous example. To claim that there is a linear correlation is to claim that the population linear correlation coefficient rho is different from 0. We therefore have the following hypotheses. H0, rho equals 0, there is no linear correlation, and H1, rho is not equal to 0. There is a linear correlation. The linear correlation coefficient is R equals 0.801 from technology, and N equals 23 because there are 23 pairs of sample data. So the test statistic is T equals R over the square root of 1 minus R squared over N minus 2, or 0.801 over the square root of 1 minus 0.801 squared over 23 minus 2, which is 6.131. Technologies use more precision to obtain the more accurate test statistic of T equals 6.123. With N minus 2 equals 21 degrees of freedom, table A3 shows that the test statistic of T equals 6.123 yields a p-value of 0.000 that is less than 0.01. Technologies show that the p-value is 0.000 when rounded. Because the p-value of 0.000 is less than the significance level of 0.05, we reject H0. We conclude that for countries, there is sufficient evidence to support the claim of a linear correlation between chocolate consumption and Nobel laureates. The examples and exercises in this section generally involve two-tailed tests, but one-tailed tests can occur with a claim of a positive linear correlation or a claim of a negative linear correlation. In such cases, the hypotheses will be as shown here. With the claim of a negative correlation, we'll use a left-tailed test where H0 is rho equals 0 and H1 is rho is less than 0. With a claim of positive correlation, there is a right-tailed test with H0 equals, H0 is rho equals 0 and H1 is rho is greater than 0. For these one-tailed tests, the p-value method can be used as in earlier chapters.